Hello everyone and welcome to our Data Zen event. Today we are pleased to introduce you Alexander Gilevich, architect at EPAM, who will be talking about how to build a movie recommendation system with Python and .NET. And my name is Andrei and I will be hosting this event today. And before we start, please put your questions during the session into the chat and we will address them after the presentation. So, Alexander, the floor is yours.
Thank you for the introduction, Andrei. And yes, a couple of words about myself. So I am a software engineer, architect, tech lead with around 14 years of experience. I mainly specialized in development of distributed applications, high-load systems, and also data pipelines and data platforms. I reside in Madrid and I've been working at EPAM for more than 7 years already. And as a side note, I love playing the guitar, as you can see, and love snowboarding as well. So we're going to start with a simple question. Why do we even need recommenders today? And the answer is pretty much simple. Because of the information overload, users today, it's hard for them to find what they're looking for. And without recommenders, they're going either to spend too much time searching or will miss inevitably relevant items, important articles, or something that they like. So recommenders help them in searching the information among all that information overload that we have today. The other reason is essentially one size fits all approach doesn't really work anymore. So personalization helps us to increase satisfaction, engagement, and retention among the users. And that has a direct business impact on the revenue through metrics such as conversion rate, retention, churn rate, and others. So we recommenders today are still useful. The other question that we might ask ourselves, which is especially relevant today, can really LLMs do recommendations? Well, they can, but they are designed to solve a different problem. Language models are not designed to inherently rank millions of items efficiently under constraints such as latency. They're not designed to store long-term user profiles or fine-grained behavioral signals. It is hard to implement real-time feedback loops with them. And essentially, LLMs are trained to predict the next token, as you know. And recommenders optimize business metrics such as click-through rate, watch time, dwell time, conversion, and so on. Having said that, we can summarize it as that LLMs essentially help users ask better questions, while recommender systems still decide which answers matter to them. But LLMs can pretty much work hand in hand together with recommender systems. And that's what we call agentic architectures today, right? The combination of both can really actually give you a lot of benefits, but we're not going to talk about that today. We're going to dive deep into the development of recommender systems. So what are the types of recommender systems? There are two mainstream types, the collaborative filtering type and content-based filtering. Collaborative filtering is really built on top of the idea that similar users have similar behavior. And content-based filtering is based on the idea that essentially in the data itself, there are features, there is a lot of characteristics which you can extract to predict relevant items. And we're going to start with collaborative filtering. So the idea of collaborative filtering, as I said, is that users with similar tastes should have similar recommendations. And when you have a lot of data it's basically the idea is that you can extrapolate this data to other users. And this approach speaks for itself because it is really good in the use cases where you have large user bases and a lot of interaction data, such as, for example, e-commerce, audio streaming platforms, social networks, and so on. And it's also good when behavior of the users matters more than any metadata, when you don't want to spend time on looking for the right features and you have a lot of data to extrapolate. So just to give you an example, so for example, you have your users such as Alice, Bob, Carol, and you have items that you want to recommend for them. And some users have ranked some of the movies, while others have not done it, essentially. And what you are trying to do is to find the right values for these missing cells. You can see question marks here. So essentially, if Alice have ranked the movie, this first movie, as like the best movie that she has ever seen, there are some movies that she hasn't watched. For example, the third movie in the list. And in this case, we are just trying to find these missing cells. And it's just done with a little magic of math, but the idea is pretty much simple. The implementation is a bit more complex, but essentially, once you learn it, you know it. So it's all based on the idea that you have your cost function and you try to optimize this cost function using gradient descent. So another type of the systems, of recommendation systems, is called content-based filtering. In content-based filtering, you try to build a profile of the user. You try to extract what you know about the users and try to feed it into your model. And this is a more flexible approach because you have control over which features matters more to you and which features you want to use in order to train your model. And the best use cases for this kind of approach is when features are really meaningful and you can extract something from your data, such as, for example, topics, keywords, music characteristics such as tempo, beats per minute, and so on. It's really good in the implementation of early stage systems with few users. And it's also good in implementing personalized search, for example. So the idea is that you train this model on top of so-called two-tower architecture. And you can see here in this diagram, in the first tower, you have your user vector, and in the second tower, you have your movie vector. And by multiplying, by taking the dot product of these two vectors, you get your prediction. So it's just a relatively simple neural network. And to create these vectors that you feed in as the input of your neural network, you can take user features such as, for example, age, gender, or country, or average rating per genre, or occupation. For movie features, you can, or for any other item features. You basically, what you do is you try to extract the features which matter the most to you, which you want to use in your model. So essentially, movie features such as year or the list of genres, R rating or duration or even text embeddings have a lot of sense in this case. And of course, I wouldn't be telling about recommenders today if I hadn't built one. So how did it all start? Essentially, on Microsoft Build 2025, they announced that you can now run Python code inside .NET, and having experience with both Python and .NET, it seemed to me like a great idea. So to be able to combine the strengths of two technologies, of two platforms in one place. So I immediately decided to put it to test on a real project. And just to give you a slight idea of what this technology, what this approach looks like. So essentially, you have your Python code, which you distribute together with your .NET assemblies. And this Python code is integrated into your .NET runtime and run in your .NET runtime. So you don't need any like APIs in between. You just run it in process. And how it happens is that the library, which is called csnakes, downloads Python binaries for you automatically, and it uses C bindings in order to call Python APIs. When you call, for example, your Python methods from your C# code. So essentially, you generate the library takes care of this interrupt layer. And what's more is that essentially it generates interrupt classes, which calls this Python runtime for you. And for you, it doesn't matter. You don't really need to care about memory management, thread management, garbage collections. It all happens out of the box. So essentially, for example, you have your Python code on the left, such as you have a module like this one, and a really convenient feature in C#, which is called source generator, generates an interface for you, which is used by you at any point of time to call this Python method. So for you, it doesn't really matter. So you call your Python methods just like you would normally do with any other method in your code base. And what's really convenient about this is if you are attentive, so coding conventions are preserved, naming conventions are preserved. So essentially in Python, there is a convention that all the arguments, all the parameters should use snake case, while in C# you have camel case. So it's all taken care of and you don't need to worry about that. So the only question was, where should I apply this approach? Where should I try it out? And as a matter of fact, the previous evening, we had a dilemma. What movie we should watch tonight? The solution really is to design a system which helps you to pick up the movie to watch according to your preferences. So a movie recommender system, the one that you probably have seen a lot of times on Netflix, Amazon Prime Video, HBO Max, or other streaming services, but without any vendor locks, of course. So, and it took me some time to figure it all out, how to build one, and essentially how to figure out how recommender systems should be trained. But during the development, I had to make a few key decisions. And those key decisions was that I didn't really have like any data about the users or ratings. So I needed some data to train my model, right? And to do that, I had to rely on the open data sets, which I could find in the internet. So the most prominent data set was the movie lens data set from GroupLens. And this data set contains enough information to start training your first recommender system. And after getting the initial approval from GroupLens, I started to train my first version of the model with it. The other key decision was that I decided to implement the content-based recommender, content-based filtering in my system. The reason for that was that I wanted my system to be flexible. I wanted to have control over which features I used to recommend any movies to the users. And I basically, as I said before, content-based filtering is really good in the use cases where you don't have a lot of data, and when you, for example, are in the early stage of your development. So for me, it made a lot of sense. And also, as a matter of fact, using neural networks is always cool, right? Because and using one in order to train your recommender is even cooler. So that was another consideration that I used. So the other key decision was that I really wanted the system to be as portable as possible, and I wanted it to function in any environment, like in your local Docker environment or in AWS. So essentially, the decision was that the system should take the raw movie length data, preprocess it, and generate training data, and then train and serve neural network. It also served like as this showcase of this technology, which I mentioned to you briefly about. And really making this system portable was on top of my priority list at that time. And essentially, the last decision was that I started with only genres as features, as main features, and then I wanted to add more features as the time goes along the development, and just starting with the genres it made a lot of sense just to have this initial first version and then iterate upon it. And in 2 months approximately, I had my recommendation system deployed to AWS. And this is the how the architecture of this system looked like at the time. And you can see here the service, which is put behind the load balancer in AWS. And the front end is implemented using Blazor WebAssembly and React.js. And Amazon EFS was used to cache the trained artifact. So I'm not required to essentially train the model each time the service restarts. The model is cached, and EFS is really convenient because you can mount this file system in any file path and just work with as a regular file path, and you don't need to use any APIs. So you just train your model and save it on some local file path, and that's it. So let's zoom into this part. Let's try to figure out how this backend process works. And we are going to start with the data preprocessing pipeline. So data preprocessing was done entirely in memory using pandas. And I implemented a Python data pipeline using pandas. And each time this service started, it essentially took this raw data set, the movie length data set, extracted the features, and generated training data, essentially used it to train the models using TensorFlow and scikit-learn. And the features that I used, as you guessed, was that I used average user rating per each genre. So essentially, for example, if a user rated like 100 movies, you can average out the ratings by each genre. So, for example, action has in general, like the user is inclined to like, for example, action movies, right? So, and this is going to be reflected in this feature. So, and movies was essentially the movie tower contained the movie genres and what in the one hot encoded way. And essentially that's it. So data preprocessing was done each time when the service started, and it was all done in memory using pandas. So to give you a slight idea of what this data set looks like, you can have a look at this slide, and you can see here that there is information about the movies and the list of genres associated with each movie. There's in the title, there's also information when the movie was released. And about the users, you don't really have much of information about, demographics, or occupation, or you only have which ratings they made, how they rated each movie separately. So, and that's really it. You need to extract all the other features using this raw data set. And this was kind of a challenge, but essentially, this is all done as part of this data preprocessing pipeline, which I told you about. And once I trained my first version of the model, I got my first issues, essentially. And the model was first undefeated on underrepresented genres, such as Western or film noir. So the solution to this problem is common, and it's just oversampling of underrepresented genres and underrepresented bucket of ratings. And you could do it using just scikit-learn and pandas, and it's simple. But once I did that, I got my next problem, which is essentially that the model was overfitted with the training data. So that is kind of an opposite scenario, which I had to resolve as well. And essentially, the solution which I came up with is that I generated synthetic users. So the idea is really that if a user likes, for example, action, in this case, they would probably also like action and sci-fi and action and crime. So I extracted from this real data, I extracted the data about my synthetic users. And I did that by using a variation of k-means algorithm. And I calculated, basically, you can calculate the distance between each set of genres, and it works like this. So, and this k-means algorithm is really universal. It is used, for example, when you try to search for the news in Google or whatever. So essentially, if you have a bunch of data, you can find the clusters of the data using this k-means algorithm. And I used the variation of this algorithm, which is called k-centroids, but essentially, this is pretty much similar to what you are seeing on this slide right now. So the idea is that essentially each movie is assigned a cluster. So for example, in this case, Toy Story and Jumanji is assigned the first cluster. And if you extract this data from the raw, these clusters of the data from the raw data, and you extract these synthetic users from the training data, you get what I call synthetic users, what I call as a center of interest. So essentially, the problem was that the user rated a lot of movies at once in the training data, which is good. But in my use case, I really wanted the users to log into the system and set as few genres, as few preferences as possible. And the system should have worked nevertheless. They didn't have to set all the genres at once. And to solve this problem, as I said, I generated the synthetic users. So in this case, you can see that, for example, instead of the user which likes a lot of movies at once, I just generated this center of interest where the user essentially can, where I can see that the center of the interest is, for example, based on some action movies, on crime movies. And if we do it across the whole database data set, you can have this kind of pre-processed training data, which is more suitable for my system. So essentially, that's how it worked. So yeah, probably it is worth a separate talk. So I don't want to dive deep into how it was designed, how it was built. You can see the source code, which is available on GitHub. So essentially, Let's switch to the second block in this diagram, which is model training. So how it was done is that I used TensorFlow, as I said, and scikit-learn to train the model and save it on Amazon EFS. And two-tower architecture was used with normalization, and that's how like the content-based filter and neural network works under the hood. And the model was trained asynchronously during application startup. So this was just a regular background service which calls Python code, and every time like it starts up, it either detects the trained model or it doesn't detect, in which case it starts to train the model using the raw data. And the neural network architecture looked like this. So you have your first tower, movie tower, and you have the second tower, which is the user tower. And you feed in both movie vector and user vector into the neural network. You get the dot product of both, and you get your prediction by multiplying these vectors, by taking the dot product of these vectors. So having said that, having established this training procedure, I had to also use the model to make inferences. And the inference it basically loads the model from EFS during the service setup if found. Again, like if it is not found, it is first trained. And .NET called Python code for inference. It basically took all the movies and used them to predict the movies which users would like. And these movies are passed as well. In the first version, the movies was loaded in the Python code itself, but now I'm passing this as a matrix from .NET code to Python. In the first, but the user vector was just passed as a one-dimensional array from backend, and that's pretty easy. You just need to generate the user vector. The other problem is that, in my system, it's still like not such a big issue, but in real large databases where you have millions of movies, you are going to inevitably have a problem where it's inefficient to rank thousands of movies at once. So you need to establish a way to filter out the movies and basically rank only those which will be relevant to the end users. And this is done using the pre-filtering stage. So the idea is that you select the candidates. For example, the candidates can be selected like based on the country where the user is located. For example, I'm located in Spain, and in Spain, users watch a lot, for example, I don't know, action movies, right? So, and similar movies are selected using approximate neighbor search. And for example, most ranked by genre, when you have a user profile built and stored in your system, you can basically use this as the information about which users, which movies, which genres the user likes. And by combining all of this data, when you selected the candidates, by combining them into a unique set and removing repetitions, for example, already watched movies, you just rank the remaining ones, and that's how it works. So basically, you can reduce the amount of movies to rank from thousands or from even millions of items to some reasonable amount, like several thousands. So that's how what I'm going to do as one of the items in my backlog, in my to-do list. But for now, it's not like really implemented. But I'm going to tell you about it a bit later. So backend architecture is also simple. It's just as ASP.NET Core API, and I cached predictions made by the model, and the backend worked as an API which calls Python code inside in the same process. So I didn't have like any Python APIs in between. So it all works really like in this, cute way, because it's really easy to spin up one service instead of like spinning up a whole bunch of services. And in this case, yeah, this is how backend actually was implemented. The front end was implemented using Blazor WebAssembly, which is a technology created by Microsoft, and React.js. And React.js components were integrated inside the Blazor app. I regretted about this decision, but anyway, at the time, it seemed like a nice decision, and Webpack was used about packaging and assembling of the front end code, but it is a single page application, and basically, yeah, that's how the front end architecture was implemented. So I mentioned that I had so what I told you about was like the initial first version of the architecture of this project. The second version, which I deployed recently to production, is was implemented in a slightly different manner, where I essentially moved this data preprocessing pipeline outside of the process, and I did it for several reasons. But the main one was that I wanted to decouple model training from the backend, and to make it more transparent, auditable, and scalable. Essentially, I implemented all of the training and data preprocessing on top of Apache Spark, and the code really works in such a way that you can deploy it to Databricks, or you can just spin up your own Apache Spark cluster locally, or use client mode of Apache Spark to just call Python, just preprocess your data without configuring or setting up the environment. So yeah, and the MLflow in the second version is used also to track the experiments and just to establish the best MLOps practices. So that's basically what I did to implement my movie recommender system, and I described you the high level how the implementation of such system looks like, what you need to do to implement that. So I built the first version in about 2 months, and basically by only having theoretical knowledge of how recommender system works, I managed to implement my own, and I learned a bunch of things. For example, implemented preprocessing pipelines in memory on top of pandas, like in the same process, and using TensorFlow and Keras to train the model. And also, of course, which is also important, usage of open data sets in production model training. And basically, I managed to implement my own movie recommender system, which solved my problem of picking up the next movie to watch based on my preferences, and that's what I'm really proud of. Along the way, there were challenges, which you just like in any problem, you solve these challenges step by step, one by one. And you for example, the challenge was that there was minimal user profile information in the open training data set, and you can extract the information that you have and train the model. And in the future, you can basically use any data that you accumulate for the users, use your system, and you train your first model, and then you use historical data which you accumulate in training the next version of the model, which might be even more accurate. And just also one thing to remember, even though the open training dataset was used, movie lens dataset was used, I also used the descriptions which are available by integrating with TMDB API. There is also OMDB API, which I am going to integrate with as well in the future. And this way you can enhance the number of features that you have about the movies. And about the users, yeah, it's a separate story. You need to carefully select what features you use for training in this kind of system. And for example, the more features you use, well, it's not really a solution. You have to be really careful what features matter to you. You need to select ones, those which have the most impact on the performance of the model. And in my case, for example, there is a problem that averaging out the rankings of the users can produce inaccurate result. Because, for example, the user might like the genre comedy in general, but they might not like when it is, like, for example, about romance or stuff like that, you know? And in general, it is going to decrease the average estimate, but you solve it by adding more features to your training data. There's also a problem that people refer to as shift of interest, because your interests shift over time. You, for example, in one stage of your life, you might like, comedy movies. In another stage of your life, you might like more like, horror or action movies. And there is a couple of solutions for this kind of problem. But in general, you have to rely on the most recent data to make the most accurate predictions using your model. So the lessons learned while designing the systems, this kind of system, was that today the boundaries between languages, frameworks, and expertises get blurred so much that you have to really be expert in every technology. And today, in the era of AI, that is much simpler, because AI really can help you to kick off your development, and then learn the implementation details along the way. And today, being an expert in everything is easier than it was before. And you by learning to implement something from scratch, you can, for example, you can specialize in not only in one area, and for example, today it's even like more relevant to not over specialize in one area, and learning new things is more important than ever today. And just as a side note, Blazor is probably not the best technology to use, especially in combination with React.js. So it's one thing that you have to analyze. And especially in this particular case, I used AI to LLM to migrate from Blazor fully to React.js, and that was done like in 2 days. So this is just a proof of my previous assumptions here and lessons which I told you about. So it's demo time, right? So rather than talking too much about theoretical foundations, how recommender systems work, let me show you how my own works, and you can access it even in your own browser. So essentially, you select the movies, for example, action or sci-fi, let's say. You just select the genres and that's it. So you get the movies which are the most relevant to you, and basically that's really convenient because you don't need to anything else. You don't need to pay for your Netflix subscription. That's how it works. And for example, let's say that we are mostly interested in watching, for example, thrillers or mysteries. Yeah, that's it. So you have your movies which are relevant to you, which you might watch tonight. So just try it out, and it works really for any genre. So let's say, for example, kids in comedy, right? So basically, for example, you just pick up the genres that you like, you set your preferences, and that's really how it works. So I'm going to work on this system to make it even more accurate and add more features. But for now, that's the version that I have. So um, you can try it out yourself. If you want, you can scan this QR code and you can try it out today. Yeah, so I'm ready for your questions. Please feel free to ask them. And yeah, that's it about how recommender system works. So thank you very much.
Thank you, Alexander, for this very detailed talk about the recommendation system you built, and we have several questions from different channels. The first one is, what issues you had with Blazor? I guess movie recommendation UI is very simple. It's a question from
Yeah.
Gregor.
So with Blazor, the main issue was that I used it in combination with React.js, and it's really not the way how they are supposed to work. And if you use Blazor or React.js, just try to use one technology to the biggest extent possible. And in this case, in this particular case, there was a lot of issues how, for example, Blazor WebAssembly works and interacts with React.js code. There was like timing issues, like how events get activated in Blazor and how I use these events to render my SPA application. So the main the integration issue which I had was between combining how these technologies work, and because they are pretty much different. And Blazor using just, for example, React.js would be much simpler, and that's what I did at the end of the day, because I had a lot of components which in Blazor were paid. For example, I needed to pay for them, or I needed to develop one myself. And for example, in this case, you can see the presentation here, right? The slideshow. So this is really, something easy that you can implement with JavaScript, but in Blazor there is no readily available component for that, which works on mobile, on desktops, and so on. So that's like combining Blazor and using open source components in my production code was really an issue. That's why I had some integration with issues with React.js.
Thank you. And the next question from Vova, is it possible to use same recommendation system in other domains, like not only movies, but coffee, music, products, vacation directions, and so on?
Of course.
We have a model, we
But
have a data source. Can we change
essentially,
the data source?
yeah, that's it. Basically, you have the model and you just change the data source. Instead of using movie lens data set, uh, you can use any other data set or any other historical data. The architecture is going to be the same either way. So you just, use your neural network in order to uh, in order to recommend what the user is going to like. But the approach is similar, or should I say even the same. Basically, you select the features which matter the most, you preprocess your data, and one important thing, and it's important in every kind of system which relies on data, you need to have accurate data. Because garbage data leads to the development of garbage system, and garbage in, garbage out. So you really just need to take care of the data, but the architecture and the approach will be the same.
Yeah, data quality is always important, especially for model trainings. And I have a question about this page with plots with comments. So here no, the previous one,
Mhm.
where you have vectors on a plane.
This one.
No. Where you have clusters and you're
Okay.
using
Yeah.
comments algorithm.
Yeah. Sure.
So here we can see a flat picture, but in reality, it's a multi-dimensional space of some features, and how we can make it flat here.
Basically, what this key means algorithm does is that it finds the clusters in the data. You have basically a lot of data, and for example, you have a lot of news coming from a lot of data feeds. So what this algorithm helps you do is it uh, analyzes this data and finds the right clusters. And for example, in the case of the news, you have, for example, one news and then the same news, but formulated in a different way. So in order to enable multiple dimensions, you just calculate the distance between data points in the right way, and that's really how it works. The
Okay,
algorithm,
we
the
just
approach
need
is
to
the same.
correctly define the distance in multidimensional space, and that's it.
Right.
And the
Yes.
algorithm
Yes.
will remains the same. I
Yes.
see. Thank you. And one more question from Alexei. What is the model size in your project?
It's a small model in S3 today, because in the new architecture I don't use EFS, but it takes about, I think, 2 MB to store both code and weights of the model. As I said, it's not a lot of parameters here. Like in total, it's about 100,000 parameters, if I'm not mistaken. Yeah, but
Quite small.
basically, what?
Quite small model comparing to
Yes, in
nowadays
comparison to
models
the
available on the
models.
market.
Yes, but the models which are available today in the market are dedicated to solve a different problem. And here we're talking about recommendations, which doesn't need a lot of parameters. But it's important to say that when you have more features, it's important to uh, adapt your neural network architecture to those new features. For example, in the near future, I'm planning to incorporate text embeddings into movie descriptions, and basically, this is going to require more parameters. So the model is going to be bigger, but it's not going to be a large language model, of course. And that's the real, a purpose of this recommenders, because They are intended to solve this small specialized task, which LLMs are not really designed to solve in an efficient way. So, yes.
And if the model is so small, can we deploy it and run on devices like mobile phone or smart TV?
Indeed, you can. And the website today is works on a really small EC2 instance. I even run it on um, micro instance, and you can deploy it to your mobile devices and use it from there. So it's a tiny model in comparison to what mobile devices are capable of running today. So you can run it literally anywhere, and that's the benefit of this kind of architecture and this kind of approach, really. So from the early days of this project, I set out on making the system as portable as possible, and uh, by the way, using ML flow uh, helps you to load this model uh, in any particular device. ML flow is really good in this case to track your experiment, but also to version your models in your production environment.
Awesome. Thank you. And one more question from Kate. How do you add new data about fresh movies to this system?
Uh, Basically, you need to separate two stages, inference and training. During training, you can incorporate as many movies as you'd like. Uh, the rule is simple. The more ranks you have, the better predictions you're going to have on various in various edge cases. Uh, but during inference, what you need to do is to load uh, during this retrieval and prefiltering stage. You load the movies which are most relevant to the users, which, for example, top 100 for a country where the user is from, or you find, for example, similar movies to the ones which user has watched before using approximate nearest neighbor algorithm. And uh, you can have as many as movies as you want. And that's also in my to-do list to uh, enrich my movie database with more movies. Basically, what you need to do is to generate the vector, and then for each movie you generate the vector, and then you pass this vector to the model. Once you do that, and in the case, by the way, of text embeddings, you need to pre-generate, pre-process text embeddings during, for example, this pre-processing stage, which I told you about. So once you do that, you are really free to feed in as many movies as you'd like, but you have to make this trade-off because the more movies you load into your model, the more time it takes to make the predictions. So there is a trade-off between the quality of predictions and performance of the latency of each request to the model. That's something that you need to take into account. But this retrieval stage is what you need to design and implement carefully.
Mhm. Thank you. And one more question from Gregor. Um, I marked only war movies in the preferences, and in results I have animations movies for kids. I guess it's because of gender relations. So, for example, drama is related to war. That's why I see Tarzan movie in the
Yes,
recommendations.
yes, indeed. And as I said, there is also a problem, an issue, a challenge with weak signals. I didn't tell you about this interpretation because it would be too much, I guess. But uh, this problem is really solved by adding more features, and that's what I'm going to do in the near future. I'm going to add text embeddings. So essentially, and I also have incorporated some other model enhancements such as negative sampling. I'm not going to dive deep into how it works, but the weak signal is essentially about this kind of situation uh, where genres is not enough uh, to make the most accurate predictions. And even if it works, for example, mostly in most cases, in some cases, it might not work as efficient. For example, kids and animation, comedy, you're going to get correct predictions. Yeah, you see adventure, animation, kids, but sometimes there is, for example, adventure, comedy, drama, right? So it's related to kids, to the genres which I selected before, but because of this weak signal issue, sometimes you get this kind of predictions. And as I said, by adding more features to your training data set, you are going to solve this problem efficiently. But again, sometimes there are some edge cases which the system currently have, and yeah, I plan to address those in the future. If you want, you can even help me with addressing those on my in my by checking my code and essentially by contributing to this repository which I have. So yeah, you please do so if you're interested in how recommended systems work under the hood.
Thank you, Alexander. And I think here we can conclude our call. Thank you all who joined our session today. And please don't forget to rate this session on our VIA community page and give our speaker a badge for this amazing and detailed session with a fruitful Q&A part. So thank you all. Thank you, Alexander, and see you on our next Data Zen events.
Thanks for having me. Bye.
Thank you. Bye bye. Have a nice day.